Good evening, everyone. Welcome back. So let's start. So yesterday we were taking a look at EDA and preprocessing. Now, EDA and preprocessing are steps we take before we start working on our ML algorithms. So, what does EDA and preprocessing include? This includes, cleaning up the data. This also includes understanding the data. So all these basic steps we perform before we get into EDA and preprocessing, understanding the data. Okay. So then moving forward, we'll take a look at unsupervised machine learning. So unsupervised machine learning means machine learning algorithm where Y is unknown. We don't know what the output is going to be. Okay. So what we try to do here is we try to get some patterns out of this data. Okay. So unsupervised machine learning is quite useful as well. Just because we don't know the output doesn't mean that data is not useful. So in unsupervised machine learning, we have various different ways. We can cluster the data. We can also create some rules. Recommendations can be provided using unsupervised machine learning. Okay, so these are the various ways in which unsupervised machine learning is used. Okay, so currently we'll be focusing on clustering. So that will be our agenda for the day. Now, clustering is grouping of data. You try to make some logical groups based on the data that is available to us. Right. So graphically, we can take a look at it. For example, this is our data. We have some data that is represented like this. So what we can do is, based on the similarities, based on the distance, we can calculate these clusters, and these clusters will give us some information. Now, that is the basic of clusters. All right. So this is used whenever we are trying to group the data together. So here our assumption is that data is unlabeled. That means we don't have any labels for this data. So we have an unlabeled data set and we are trying to work on it. Okay. So this is a centroid based algorithm. So we try to get some centroid values out of this. Okay. So these centroid values, they don't necessarily have to be data points. Okay. They can be any value that we need. And another thing in k-means clustering is we have to define the number of clusters beforehand. That means however many clusters you have to define them. Without defining these clusters, you cannot do the segmentation. So we'll be focusing on k-means clustering, and then we'll take a look at the hands-on of k-means clustering. And we'll be focusing on taking a look at how k-means clustering is used within security analysis. So in financial security, we have something we call as portfolio. Now, portfolio is your collection of investments. So you have made some investments. You have made investments in different companies. You have bought stocks. You have bought whatever financial instrument is available. You have bought. Okay. Now these portfolios, they can include your stocks. They can include something we call as the Roth IRA. They have 401ks. Okay. So there are a bunch of different values we have within this cluster, within this portfolio. So now what we are trying to do is we are trying to optimize our portfolio. So whatever portfolio is available to us, we are trying to optimize that. So what we are trying to do here is we have a data set which is depicting the price of shares for different companies and how it is changing over time. So what we are trying to do is we are trying to group these companies. And based on the groups, they can be used for investment. Right? So we can select what companies you want to invest in your portfolio. Now, portfolio is very important, right? Because a lot of people depend on these portfolios for future funds. They depend on these portfolios for their retirement funds. So it becomes increasingly important for that. All right. So that is why we are trying to optimize it. That is why we are trying to find the most suitable investments you can make. And these investments, again, they will be based on the number of groups you can split them into. Based on these groups, you can decide if your portfolio needs updating or not. And whenever you're updating your portfolio, you are debating a lot about where to put your money, because at the end of the day, everybody has a limited amount of money. You cannot just, spend all your money on wrong investments. If your portfolio is not working properly, then you're obviously going to be facing a lot of issues, right? So that is what we try to do here. So let's understand k-means clustering. So k-means clustering we perform two tasks with it. These are the two primary tasks we perform with it. The first is to determine the best value of centroids. So since this is a centroid based algorithm, we are trying to determine the best value for these centroids by an iterative process. We are iterating through some values and we are trying to determine our best k-means. Okay. And then we are assigning data points, whatever data points we have, to its closest k center. Okay. So as you keep assigning more and more data points, your centroid values may start changing. Okay. So based on that, you keep updating your number of clusters up until the point where you find the ideal number of clusters. Okay. So again, we have seen that if you have some data points, now let's say this is an example of data points. You have some data points here, you have some data points here, you have some data points here. This is fairly simple for us to cluster. You can keep iterating through, no matter how many data points you have, you can keep iterating through these clusters. Okay. So what are the steps we follow for these k-means clustering? Okay. So it's an optimization based algorithm and we try to minimize the within sum of squares. That means within the cluster, you're trying to determine the ideal number of data points and the ideal number of clusters. So you select a k value. Now, if you give k equals to 2, you will get 2 clusters. If you give a equals to 3, you will get 3 clusters. So this is how you try to determine the ideal number of clusters. And then you try to find the distance between all data points to all of these k clusters. So you are trying to determine these distances for all the clusters. Every single cluster, that is every single centroid point is there. You measure the distance for every single data point. That can be a little bit of a repetitive step, but that is the formula we use. Those are the steps we take. And then we try to add them to their nearest k. And then you recalculate new centroids. After adding data points, you can calculate this centroid again. These centroid values are constantly getting updated. Okay, based on how many data points you're adding to your cluster, these centroid points are constantly getting updated. And then you keep repeating these steps. Again, you enter in a loop. You enter in this loop until the point where the algorithm stops converging. Now you might have a scenario where a data point is constantly moving back and forth between two centroids. So that is why we are doing these recalculations. That is why we are constantly calculating how many clusters we have. And based on these clusters, we can determine the correct value. Now, once you stop converging them, once these data point stops converging, then you determine the ideal number of clusters. Okay, this convergence stopping is very important. Without the convergence stopping, you might have a scenario where the data points are constantly moving and you're never able to determine the ideal number of clusters. Okay, so let's see Now here we try to find the within sum of squares. So what is within sum of squares? Within sum of squares is basically the square distance between data points within a cluster. So within sum of squares, you can use distance metrics like Euclidean, Manhattan, Mahagonolus, and there are many different ways in which you can calculate this within sum of squares. So basically what you're doing is you're trying to determine the ideal number of clusters by taking the distance. Okay. So just 1 second, we'll be right. So within sum of squares. So we can have two different ways in which we can calculate this. So you have within sum of squares and you have between sum of squares. So within sum of squares calculates the distance of data points to the centroids of a cluster. So you're trying to see how tightly packed your cluster is. The lower the within sum of square value is, the more tightly packed your cluster is. Okay. And between sum of square is the distance between two clusters. So you try to determine how close or how far away your clusters are to each other. Okay. So that is the two methods. Now, mainly we'll be focusing on within sum of squares. Between sum of squares is not as useful. Okay. So using within sum of squares, you determine the within sum of square for each cluster. So if you have k equals to 3, you will have within sum of square of cluster 1, within sum of square of cluster 2, within sum of square of cluster 3. So what you do is you add them up. So you get the total within sum of square, which is the distance. So how is this total within sum of squares useful? This will help us determine the ideal number of clusters. This will help us determine the ideal number of clusters. Now these cluster values can change. So we use something we call as the elbow curve. This elbow curve is the most basic way in which you can calculate the ideal number of clusters. So let's say, for example, we have defined some cluster values. We are saying take clusters from range 2 to 11. Once we define that, we get k equals to 2, 3, 4, all the way up until 10. Then you calculate the total within sum of square of these clusters, 3, 4, all the way up until 10. And then you plot it. So you get for 2, 3, 4, 5, 6, like that. So you plot a straight line from point to point. So here at cluster 4, we can observe a elbow forming. Now this elbow will determine the ideal number of clusters. Wherever this value is found, that is where we define the ideal number of clusters. Okay. So similar to this, we can also calculate something we call as the silhouette score. Okay. So silhouette score. Silhouette score is also useful in determining the ideal number of clusters. So this is ranging between -1 to 1. Okay. So how is this useful? So again, this is calculating the silhouette coefficient. So silhouette coefficient. This is going to give us how similar data points are within a cluster. Okay, so we can determine how similar these data points are within a cluster. And to calculate, the formula is given as this. So you have B of I minus A of I divided by max of this A of I, B of I. So A of I, what is A I? So this is the average distance for a data point I and all other data points within the cluster. Okay, and then you have B of I. B of I is the average distance of I and to all data points not within that cluster. So basically what you're doing is you have defined your cluster, right? So within your cluster, you have some data points. Now what you're trying to find out here is first the distance that data point has to all the other data points that are present in its cluster. Okay, so you calculate the average of the distance. You find the distance for all the values and then you divide it by the total number of data points. Similarly, afterwards, you calculate the distance of B. The B distance is represented as the distance between I, our data point I, and all the other data points that are not present within this cluster. So whichever data point is not present within this cluster, you calculate the distance and then you take the average. So you're taking the average distance. Okay. So let's say, for example, you have this cluster. And we have this data point I. So what you do is you calculate the distance this data point I has to all these other data points. So you calculate this distance, this becomes A or I. This is distance of I to all data points divided by number of data points, because you're taking the average distance. And then you have another cluster here. What it will do is it will calculate the distance from this to this. So you get different distance. So this is your B of I. Distance between I to all data points not within the cluster, divided by number of data points not within the cluster. Obviously, you will not divide it by the total number of data points. So this is how you calculate the silhouette score. The silhouette score, again, like we said, discussed earlier, it ranges from -1 to 1. That means what? At -1, this is the worst possible cluster. So if you have the value -1, you can say that your cluster is not very good and you should not proceed with it. Okay. And then if you have value of 0, this means overlapping clusters. That means your clusters are overlapping with each other. So this is where you're facing the issue of convergence. So if you are calculating the silhouette score and you come across cluster silhouette score as 0, that means you can probably do better. And if you are getting 1, this is the best possible cluster. So within this cluster, all the data, the cluster distance that within sum of squares for a cluster is very less, and the distance from one cluster to another cluster is very high. Okay. So you don't use just silhouette score, you use silhouette score plus your elbow method. So use both of them. After using both of them, you determine the ideal number of clusters. Okay. So this is going to give you a better decision because then you have two things that you can use to verify your clusters. Okay. So let's see how this works in real life. So this is a data set. So let's just restart our kernel and then we'll get into it. So we have already covered this data set before. We have already seen how we can use this data set before. Okay, so let's just quickly go through it. You can import the necessary libraries. Okay, you can import whichever libraries you find are necessary. So we are importing for now pandas for reading data frames, NumPy for any numeric calculations or array requirements we might have, matplotlib for plotting, and C1 also for plotting. So we'll import our data set. We'll take a look at the data types for our data set. We'll get the shape. Now you can see here that the data set has 10 lakh entries. So this is a huge data set that we are working with. So using this data set, we will get a lot of information. But what we can do here probably to fasten up our speed would be to take a subset of this data. Okay. So we'll get the first 5 rows. We can see the symbol of the company, the type of data, security it is, the date, the previous closing value, the opening price. The previous closing value and the opening price are varying. What is the highest price that they have achieved on a particular date? What is the closing price on that date? What is the average price throughout? What is the quantity being paid? What is the turnover of that company in lakhs? What is the delivery quantity? How many stocks are they delivering per day? What is the delivery per stock? Okay, per purchase. So we get the columns, and then we can also do a basic EDM. So this will take a few seconds to happen because we are taking a larger data set. Okay, so now our report is generated. So we can probably uh, take a look at this report as well if we need to. We have already covered this, so we can probably not spend too much time on it. We can just go through it. Okay, we have already seen that we have a situation of high correlation. That means these values are very correlated to each other. Okay, when we obviously check for null values, we see we have null values, we'll drop these null values. We check for duplicated values, we can drop these duplicated values. And then what we can do here is we can probably again recheck the shape. So we notice that we had 10,48,575 data points, data rows. Now we have 10,46,420. What this means is that the rest of these values have been dropped from here. However many NA values were there, they are dropped. However many duplicated rows were there, they have been dropped. Now we'll apply the normalization function. What the normalization function is used for? It is used to make the data unitless and scale free. We don't have to worry about the data having a larger scale. You can simply just, what do you call it? You can simply just reduce the scale to a smaller number. And whenever we are doing means what do you call it? Normalization, the data is ranged between 0 and 1. Okay. So that is what we'll do here. Okay. So we'll apply normalization function. We can take a look at the mean, mode, standard deviation, all these values. We'll select our numeric columns. So these are the numeric values we have. So now here you can see that the value ranges from very high within this cluster. So what we'll do is we'll apply the normalization function. And then we can look at the change in the values. We can also take a look at the change here. We notice that the values have changed a lot. Similarly, we can apply standard scalar. Standard scalar will make the mean 0 or near 0. And standard deviation would be 1. So we can apply these concepts. Okay. So we'll do standard scaling quickly. We'll apply and we can see that the values have changed. Similarly, we can also check for the data flow. And we notice the values have changed. So now what we'll do is, instead of directly going into the code, what we'll do here is we'll reduce the size of the data frame. So we'll take df underscore norm, for example, and we'll take only the first the first 10,000 rows and all the columns. Okay, so now if I go here and take a look at df underscore norm, we have only 10,000 rows. We are doing this because 10 lakh entries is a lot of entries. Similarly, we can do the same for our standard scaled data. So we can also see how having different standardization method can affect your clustering. Is it better to go with normalization in this scenario, or is it better to go with standardization? So first we'll go with normalization. So we'll call this AWS norm. We'll define it. This is where we'll store all our total sum within square values. We can define K. K is going to be all number of clusters between 2 and 10. You can also go to 20, 2500 depending on your problem. So here we'll use a new library. We'll use Scikit-Learn. Scikit-Learn is also called as Scikit-Learn, and this is used for scientific related calculations. And this is also a very important ML library. A lot of the models are built using Scikit-Learn as the base. So going forward, we'll import it. From this, we are importing k-means. You can also import k-means plus plus. It is a more intelligent way of doing k-means. So, but for now, we'll carry on with k-means. So we'll import it. We'll have to ensure here that we are putting the correct name. So you want it to iterate through this list of k. So if here I say k, this will give us a list 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the clusters we want to form. Okay, so this determines the ideal number of clusters that we want to form. So we'll go from 2 clusters and we'll go all the way to 10 clusters. So what we'll do here is we'll import this, and then here within this for loop, we are creating a variable called k-means. This k-means variable will take this k-means class from Scalar as its function call, and within it will define the number of clusters as I. It will go through this list and will apply this on the normalized data set, and we'll try to find the total within sum of squares. So let's run this. We can check. So this is the total within sum of squares for our value. So here you can see that as you go, of course, as you go, the number of clusters will keep on reducing. Similarly, we can plot it. This should be long. So we can plot it. So here, this is our elbow curve. Now, based on the elbow curve, clusters 3 and clusters 4 look the most promising value for clusters. So now what we'll do is from Scalar, we'll get a silhouette score. So here we'll define a silhouette average for normalized data variable. We'll create an empty list and we'll try to find the ideal number of clusters. Okay. So here we'll try to find the cluster labels as well. So let's run it. So here we have to change session. So here we'll change the variable name and then we'll try to calculate a silhouette score. So this will plot the silhouette score alongside with it. So let's wait for this to happen. Now we'll use the silhouette score in combination with the elbow curve to try to determine the ideal number of clusters. Where is this error coming? This. Okay. So let it run. Since we have 10,000 data points only, it should not take a lot of time. So here we have the silhouette score. Now the silhouette score is highest for 2 clusters, but here we don't see that elbow curve. But again, it is quite high for 3 clusters. And here we are seeing that 3 cluster is where we are observing some change. So what we'll do here is we'll go with 3 clusters. Okay. So let's fit for 3 clusters. So we'll get our model labels. So here what we'll do is we'll convert it to a series and we'll create a column for clusters. Okay, we are getting some warning. We can ignore that warning. So now if you take a look at it, we can see that it has defined the total number of clusters. Now similarly, using this same code, we can do the calculation for standard scale. So we'll do that. So let's take the same value for k again. We don't need to change it. We'll just change our data set name. So here our data set should be df underscore sc. This should be TWSS underscore SC. So we'll determine the ideal number of clusters here. We'll take a look at it and we can compare the results. Okay, so 1 second. So this is the cluster distance we are getting for df underscore sc. We can already notice that there is some difference. So let's try to plot it and see if the plotting is any better. So again, the plot looks very similar, right? It looks very similar to our previous example. So what we'll do here is we'll again try to calculate the silhouette score. So let's calculate the silhouette score and then we can determine an ideal number of clusters. So we'll change this name here. We'll ensure that we are using the correct data frame. And we are ensure that we'll plot the correct data frame. Okay, so let's let it run. So now here we notice the difference. Now we have seen that silhouette score ranges from -1 to 1. Wherever it is 1, it is a perfect cluster. Basically, your clusters are tightly packed and the distance between the clusters is very different. So here we can notice that at cluster 3, it is nearly 1. So based off of this silhouette score and based off of a fact that here we have a pretty dramatic curve from cluster 3, cluster 4, the curve is quite large. This curve is quite large. So based off of this, we can say that n equals to 3 should be the ideal number of clusters. Okay. Similarly, you can keep increasing the data size. So if we increase our data set size to, okay, let's do one thing. So we'll run this again. We'll convert it to a data frame. We'll get it. Now here we have 10 lakhs. So here what we'll do is instead of taking 10,000, we'll take 50,000. Here we'll take 50. So now we have 50,000 records. So what we can do here is we can run this value again. So we'll take k-means, let it run for 50,000 iterations. It should not take too long because for 10,000 it took a few seconds. So it is done already. So now these values have changed. Obviously, these values have changed as they were expected to change. Now let us plot it. So again, based on the plotting, we can probably see that the clusters are probably going to be the similar clusters. So let's try to use the silhouette score. What is the error? Why is this error coming? We are plotting for the wrong one. That's why. Let's wait for it to complete its plotting. So it is taking a little time, but that is to be expected for 50,000 data points because it has to calculate the distance. So we'll wait for it to fully calculate the distance. This is taking a little longer than I expected. So again, we were able to get the elbow curve quite fast. Now silhouette score is taking just a little bit of time. So once this is done, we can determine the ideal number of clusters. All right. So we have found the ideal number of clusters. Again, similar result to the previous one. So the ideal number of clusters is probably 2, or we will go with 3 because 3 is showing a more of a shift within the elbow curve. So using this clustering, we can segment our market, and this segmentation we can use to determine which portfolio to focus on, which segment of the market. Okay, so this is k-means clustering. So with this, we finish today's session, and then Tomorrow, we'll start taking a look at a different business problem with a different ML model. So thank you everyone for joining, and I hope you have a good evening.